All right, great, thank you. So I'm going to be reviewing some of the work that we've been doing at the University of Maryland over the last few years. I've broken it down into two parts. We're going to be talking about some force measurements that we've been working on, and specifically the role that patch potentials may be playing in our experiments. And then I'll be talking about a new torque experiment that we've been working on. And so the work here is done by I'll call it Team Casimir. We've got two graduate students, one working on each project. They've been doing an excellent job, as you'll see. And then we also have an undergrad who's been working on some computational things related to this Casimir torque project. So first I'll talk about some of the force measurements. So as was pointed out in the first talk today, if you're trying to measure the Casimir force, there's a lot of other things you have to deal with. So in general, we say, well, the total force, we're going to measure some force. And so it's going to be the Casimir force plus a bunch of other stuff. And so hopefully we can minimize all that other stuff as much as possible. And so one of those things is electrostatic forces. And so the first thing we think to do is just try to ground out these samples. You've got two metal samples, so you try to ground that out. If that doesn't quite do it, then you might try to apply some bias potential so you can minimize that sort of electrostatic force. But as we also heard, there's a lot of other forces that are still there, even if we try to do that. And so one example are these kind of patch forces. So that's something I'll get into with a good bit more detail as we continue. But if we go back just to the earliest Casimir force experiments, so this was also mentioned, this work by Munday. And so he actually pointed out a number of these different types of electrostatic forces that you would see here. So you've got chemioabsorbed species here that can be modifying your electrostatic interactions. You have static charges that build up here and give you additional forces. And then there's also there's a potential difference perhaps between your two metals. So if they're different metals, then you can think about that pretty easily as your work function difference. Apparently I should be giving a talk now or something. Sorry about that. So then there's also just a general, you've got two different metals, and there could be some potential between those. And then maybe about 20 years later, we have some work by, and hold on a second. Looks like my calendar came up, it confused things there. Let me just start that again. And so in this experiment, Van Blokland and Overbeek were looking at two chrome materials. This time are two chrome objects. This time a plate and a sphere rather than two plates. And here they were actually controlling the potential difference between them. And the idea is that you could basically tune it so that you'd have zero voltage between them. They still ended up finding that there was still something on the order of 10 or 15 millivolts difference between them, even though they're the same material. But this is, again, kind of an effect, an electrostatic effect that started playing a role here. So then we can jump forward to some of the more recent experiments that we've seen. So this was also mentioned at the beginning. So these are the experiments from the Yale group. And they were looking at these Casimir force measurements between a sphere and a plate, and depending on which types of samples they used, they found that the surface potential across the plate can vary. And sometimes there will be situations where the variation is relatively small, and there's a small force contribution here, so you can basically measure the Casimir force, and it's not much of an issue. And then on some of the other samples, it actually became an issue. Where the measured force then was kind of dominated by an electrostatic contribution. This has also played an effect in some atomic physics experiments, and looking at patches in metal surfaces and how that can modify ionization of atoms as they approach a metal. And then recently there was work analyzing metal surfaces for Casimir force experiments. And in this particular work, it was found that the electrostatic patch potentials were relatively small, and the effect shouldn't be influencing the forces. And so we wanted to see what this looks like for our experiments. So we're going to be using a technique which was also used in the previous ones called Kelvin probe force microscopy. For people that aren't familiar with it, it's kind of like this, only much, much smaller now. So this goes back to work of Lord Kelvin, where he's looking at, starting with looking at two different materials, and as you put them together, two different metals, there'd be some charge transfer between them. And so there'd then be a charging effect. In the case that we have now, we see a force. So you can shrink this down about 1 million times or so. You can use atomic force microscope, and you can do similar sorts of experiments where you can apply a voltage or bias to a tip and look at the interaction with the surface. And this was developed shortly after the atomic force microscope started being used, where you could start looking at potential differences between different objects. All right, so there's a bunch of different flavors, if you will, of Kelvin force microscopy. And so I'm going to talk about two kind of common ones here. One is an amplitude modulated version of Kelvin probe force microscopy, and the other one is a frequency modulated, or in the case of some of the stuff that we're doing, it's a heterodyne method, but I'll just kind of lump them together, basically as things that go as the derivative of the capacitance, and things that go as the derivative squared of the capacitance. And so with these different techniques, so with the amplitude modulated one, I guess with both of them, you're getting contributions from both the tip of your cantilever and of the actual cantilever itself, because there's some sort of distance dependence, it's electrostatics, you've got interactions with both of these things. Now, with the amplitude modulated, because it goes with the derivative of the capacitance, the first power, you end up getting more contribution from the cantilever than you do the tip, because you've got this very large cantilever here and a relatively small, narrow tip. So if you have something that varies more quickly with distance, then the closest interaction starts to play a bigger role, and so you can have a larger interaction just between the tip and the sample. So kind of qualitatively, you can think about it this way. There's some nice work back in 2005, kind of comparing these quantitatively, these different methods, where you can see that you get kind of improved spatial resolution here. You can more clearly see this the transition here from one material to the other using this frequency modulated method. And there's also been some more recent work, I guess a lot of different works, but here's another example, looking at some graphene layers and how the potential varies as you go across. And so you also see that in addition to the spatial resolution that you see improved here, there's also improved contrast that you're getting when you start using these frequency modulated heterodyne techniques. So when we're deciding what to look at for our samples, we decided to go with one of these sorts of methods for these reasons. So here's an example of some samples that we were using. So these are gold samples that were deposited by electron beam evaporation. And so here we have topography. Here's some amplitude modulated KPFM, and then the heterodyne KPFM. And you can see that you start to reveal smaller features in this sort of method. And you can also see that you're revealing larger potential variation that you get as well. Again, because you're really looking at the interaction between the tip and the sample rather than a combination of tip and cantilever. So we then wanted to look at different samples to see if we could find which samples would have a smaller patch potential effect for doing these types of experiments. So we looked at E-beam deposited gold, sputtered and annealed, and also template stripped gold. So this is a type of process that allows usually very smooth gold samples. And you can see, interestingly, that all of these give patches that are about on the same order of magnitude for their overall value, but the spatial variation is very different. And the spatial variation is important when it comes to determining the effect of patch potentials on any sort of force measurement. So you can go through a theory of calculating these. So we just took a theory from the literature where you can make a correlation function based on where you have these spatially varying potentials. And then you can calculate, if you assume that it's the same between two plates, and then of course, then translate that over to sphere plate geometry. And then you can calculate that, so there'd be a bunch of curves here. So this is looking at a pressure based on this patch potential as a function of the distance separation here. And so here are some of the theory papers that we use to do these calculations. And so you can see that for the measured range, so this shaded region here, these are from a bunch of different samples using different methods. So we got a range of patch potentials here. And so then also we have, for comparison, the results that we got on the sputtered ones, which are what I showed you earlier, using either the amplitude modulated or the heterodyne potential. So for our sample, we found a lot of variation, so it's really important for us to understand those whenever we make measurements. So those were all on wafers, so on the plane, but obviously you have an experiment, you have a sphere and a plate. So we wanted to see how they differed on these different materials. And so this is not a sphere that would be used in an experiment, this is just for a proof of concept to see. But we deposited gold in the same manner on both of these objects. We had a sphere that was attached to a plate, just so we could look at what the patch potential variation is from one surface to the other. And so those are plotted here. And so you can probably see, even just visually, you'll look at the color looks slightly different between these two. So you see, even depositing them in the same manner, that we are getting some differences in the way that the patches are distributed here. So it's important for us to understand that when we make our measurements. So the other thing is, how does humidity affect patches? So the experiments we're doing are in ambient conditions. And so we wanted to see over the course of a day, or if we purposely change the humidity, how that affects it. And so this is these are the patches here under I believe it's about 20 to 25% humid environment, and we're going to start letting it get more dry. But here's the autocorrelation function, so the autocorrelation between the different values of the voltage spatially distributed as a function of the separation that we have between the pixels here. And so basically you're going to use this function in order to determine what the electrostatic force would be based on patch potentials. And then as we start decreasing the humidity here, we see that the patches start to change. And so there's a change in the long wavelength range. There's also a change in the short wavelength, sorry, not wavelength, the separation region here. And they're actually kind of counter to each other. And so they affect the force in different ways. But you have to go through all of it in order to determine what the actual effect is for the samples. So that's something else that we're keeping in mind as we continue on with this. All right, so that kind of concludes the first part, talking about some of the effects that we've been seeing in electrostatic patch potentials. And so now I want to talk a little bit about the torque. So the torque was talked about in the last presentation, so I don't have to say too much about it. Basically, we have our normal Casimir effect. We have the fluctuations are confined between two materials. If these are birefringent materials, they have an optical axis and a different index of refraction depending on the direction of the E field. And so then there will be the 0 point energy here now depends on what the orientation is of these objects. So if you have an energy that depends on an angle, you have a torque. And so this is pointed out by a number of people. I guess probably the first one that I've seen here is from Protegian and West back in the early 70s. And this was in the non-retarded regime, so for close range, kind of the van der Waals limit. And then Yuri Brosh had a nice full formalism that would calculate it out for within the retarded regime as well, a more general formulation of it. And if you look back even at Landau Lifshitz in textbook now, where they talk about these force interactions, there's a little footnote at the bottom of one of the chapters when talking about basically the Casimir interaction, saying that if you have anisotropic bodies, you should in general have a specific effect, namely a torque. So there's this kind of textbook stuff that's sometimes kind of overlooked, but it's an interesting phenomenon. All right, so I was talking with Rudy this morning over breakfast, and he was asking, there's people have been talking about the torque, but we haven't really seen measurements of this, and so why is that? And I'd say because it's hard, like most Casimir force experiments. But there are a couple of other things that make this particularly hard as well. And so the torque is weak. So it's even a weaker effect. It's kind of a little bit hard maybe to compare forces and torques, but I would say that they're at least equally hard because of being weak. Again, you want small separations, just like with the Casimir force. And you also have to deal with parallelism. So you want to keep two plates parallel like you do for Casimir. For Casimir force measurements, you usually switch to a sphere plate geometry, which helps, but that's harder to do if you're looking at a torque. So also we can look at the kind of free energy per unit area. So this is the way it would vary as a function of angle. And so you can see there's a relatively small variation here. This is microjoules per meter squared. So you want to take this and you want to take a derivative of it and look at the torque, and you get something like this. So now we're looking at something that's more on the kind of nano newton meters per meter squared values here. And there's a power law decay here as well. So these are looking at, you're thinking maybe tens of nanometers as ranges you might want to try to measure this. So the way that we're thinking about this, so one solution might be using pneumatic liquid crystals. So these are materials, they're molecules basically that have a long direction and a short direction that have a different index of refraction associated with them. And so the thing that's nice about this is it can serve as a birefringent material, and it can also serve as a sensing, kind of as like the torsional rod that you would normally be thinking about. And so these things, when you put them together in a bulk, they can be described by an elastic twist constant that gives you a torque per unit area that goes as this elastic twist constant times the angle over some thickness that you have of this bulk crystal. And so for a common liquid crystal like 5Cb, this constant here is something around 5 piconewtons. And so if you pick a thickness of your liquid crystal of about 50 microns, you get the sort of relationship here between the angle that you'd measure and any sort of torque that might exist to do the rotation. So if we're thinking about an experiment to do this, how might that look? And so the idea would be that you take a liquid crystal. So liquid crystals are common in display technology, and usually the way that this is done is you take, it's easy to fix the boundary on a liquid crystal. So you can take a material, you basically can rub it, and you put the liquid crystal down and it'll tend to align on that. So you take two of these materials, and you cross them, and you get the liquid crystal to rotate as it goes through. So if you have just one material that has a fixed boundary, like that, you have this. And then up here, let's say it's free to rotate, so we're not making any specific boundary on it. Now, what we can do is we can bring down another material here that has an isotropic layer, so one that doesn't have any reason to cause a torque. And then behind that isotropic layer, we'll have our birefringent crystal that would enable some sort of torque. So then what would happen is as you bring them into contact, if there's a strong torque, it'll rotate. So just like this. So then it would tend to align with the axis, the optical axis of your birefringent material, which would be behind that. And so we can take a look at this again for some typical sorts of numbers here and look at how much would that axis of rotation, how much would the liquid crystal rotate going through this bulk liquid crystal here, given various values that we might calculate for the Casimir torque based on different combinations of birefringent materials with a different layers of a spacer layer here. And so you can see basically on the order of several degrees rotation over tens of nanometers of separation for all these materials. And so we were putting together an experiment for this. This is kind of schematically what it looks like. You've got light that comes through, goes through a polarizer. You've got your birefringent crystal. Sorry, actually the birefringent crystal is in the bottom. This is inverted. We've got the alignment layer here to align one side of the liquid crystal. The liquid crystal's here. Then we have our spacer layer and our birefringent crystal underneath. And then we have an analyzer down here to look at that we can then rotate and see what the polarization of the outcoming light is. So I won't go through all the details here. But basically, the birefringent material will cause the polarization to rotate. You can use a Jones vector formulation if you want to. Basically, you put in some sort of input polarization. It gets twisted through the liquid crystal, and then we can have it go through an analyzer, and we can look at the final signal here to detect out what we get. We can look at that as a function of the wavelength of light as well. That gives us another kind of parameter here. So this is not Casimir torque measure data. What this is a calibration run that a student did a couple of weeks ago. So this is looking at a known amount of twist. So we've specifically twisted it so that we know what we're looking at. And then we measured basically the intensity as a function of the analyzer position and also the wavelength. So we've got a spectrometer that we can use that, and then we can fit the data to a model and determine what the sensitivity of our experiments are. And so basically the director twist we can measure down to a little bit under a degree right now, which would correspond to torques on the order of nanonewtonmeters per meter squared, which is right in the range of what we're looking to do for our experiments. So with that, I'll go ahead and summarize here. So the first part we talked about patch potentials and how those might be influencing our force experiments. And then we've decided to go with a technique that enables us to look at the surface potentials based on the capacitance, the second derivative of the capacitance, because we feel it gives us a better resolution of both the voltage and the spatial dependence. And then also we have some experimental attempts going on right now to look at this Casimir torque. So thank you for your attention.
Questions? Yeah, Kim, please.
So, when do you think you'll have some results on the Casimir torque?
Well, do you want to ask me or my grad student? We might give you different answers. No, I'm optimistic. I mean, he's been working on this for a couple of years now, and there's been a lot of progress in the last year. So fingers crossed later this year we'll have something interesting, but you never know.
Okay, yeah.
Could you please return to the slide about the Casimir force measurements for 13 years?
Sure, which measurements?
Physical review letters.
Physical review letters. I'm not quite sure which measurements?
Before. This one.
Oh,
no.
sorry. This one?
This is one.
Okay.
Here you present the calculation in the framework of Drude and plasma models. You have taken this from the original paper.
Yeah, no, I'm not claiming to have done any of this. These are all paper. I'm just taking some images from papers. Yeah.
But in this paper, this value are calculated for simple Drude and plasma models, which without account of optical data. If to take the real optical data of gold, the results of calculation deviate significantly from the simple Drude and plasma models. And the results of the force calculation for both models at small separation are much larger in magnitude than the measured as a result. There is no electrostatic source which could bring the measurement data in accordance with both variants of theory.
So my only point here actually for showing this was just that there's measured data here that in this case, the experimental data doesn't seem to correspond with any sort of electrostatic contribution. And in this case, the data seems to correspond well with some sort of electrostatic contribution. So I'm just showing that on different samples, you get different results for how much electrostatic contribution you might get.
But for this experiment, there is no electrostatic force which can bring the data in accordance with prediction of both systems. So
Okay, fair enough. If you just pass it on. Yeah.
I was just wondering if you would like to do torque measurements but with the sphere plane geometry.
Yeah.
You might be able to make yourself an artificially anisotropic medium on a sphere, say a dielectric or a gold sphere, by laying down a number of parallel but of course curved nanotubes stuck on the surface. And so you could create yourself, you can have your cake and eat it, I think, have a highly anisotropic medium of some sort and also a spherical geometry. I don't know if this is any use, but it was a thought.
Yeah, no, it would be interesting. I think, I mean, there's been some work from Amar's group that was looking at, the lateral sort of Casimir effect. And so there you've got, gratings that are kind of like that. I think that going to the nanotubes would be a nice way that you're really getting something where the geometry is probably playing less of a role because they're so small and closely
I think you
stacked.
get much more anisotropic behavior out of nanotubes and grating.
Yeah, I think it would be an interesting thing to try. It comes down to what's easier to do, to put a bunch of nanotubes on a sphere or a different experiment. But yeah, it's an interesting idea.
Rudi first, I think.
Yep. So one question, patch potential is of course a disorder. And the question is this quenched or annealed? And how do you know?
I do not know. Sure.
Because it behaves differently. Annealed means as you push the two surfaces together, it will rearrange. And quenched means that as you prepare the surfaces, it will remain like that all the time. And
Yeah.
that gives different interactions.
Yeah, no, it's a great, great comment. So with what we were doing so far, we were just basically preparing samples the way we normally would for Casimir force experiments. And so when I refer to annealed here, it's just an annealing treatment. We didn't really look at annealing versus quenching or anything like that. We just said, let's prepare a bunch of different samples the way that we might think to do them whenever we're making our Casimir force measurements, and just measure the surface potentials to see what kind of variation we get. But that's interesting. It might be another way that we could modify that. Yeah.
And a very short comment. So when you talk about anisotropy, it's true, the free energy goes as cosine squared of the angle. But if you look at the anisotropic shape contribution to that, it goes as 1 over sine of the angle, which is much stronger. So I would think it would be easier to see anisotropic shape torques than anisotropic dynamic properties.
Perhaps. Yeah, I don't know. I hadn't thought of it. That makes sense. I guess the dependence on the thickness is also, or the separation, would probably be the same for those two cases, I would assume. So,
That would be the same, yeah.
okay. So yeah, so if we can make geometrically anisotropic without sacrificing our separation, that would be interesting to try.
Okay, I think, yeah, Vladimir?
Now there are experimental configurations where the predictions of the Drude and plasma model approaches differ by a factor of several tens, several hundreds, several thousands. One example is experiment by Dumont and Decca. Isn't it meaningless in this situation to consider try to explain this difference by the contribution of patches? If predictions are differ by several thousand, it is impossible for sure.
Well, you might notice I didn't mention Drude or plasma in my talk here. I was basically just talking about trying to measure an experimental artifact that we have. So whether or not that can account for that, I mean, I showed you numbers, I guess, I didn't really go into any detail with what the values are. Actually, I guess I've gone too far back. But yeah, so I mean, with the, in the regions that we're looking at, some of the patch potentials are comparable to the difference between the Drude and plasma models. But I think as Steve Monroe was saying earlier, I mean, I don't think it also really matters whether you're talking about Drude or plasma. It's really something in between in real life. So we're not really looking into that.
Okay, I think we have, yeah, Umar from the back.
I was just going to ask for your comment on, the patch potential measurements were done in air with different humidities you pointed out. So could you comment on how it will translate to the experiments which are usually done at high vacuum?
Yeah, so in general, so there's two things that are going on. So one, you might think that when you go to vacuum, or I guess maybe I should say going from vacuum to air, when you go to air, usually you do get a little bit of a wetting layer, which actually suppresses it a little bit. So in air, you tend to get a little bit less contribution from patches. It also changes the distribution itself, whether they're kind of small patches versus large patches. But we don't quite understand the results yet, so I wouldn't speculate too much on that. But it does depend on the humidity.
Okay, yeah, there we go.
Is the effect of humidity reversible? So if you change it back, does the result go back to the previous ones? So that's first. And second, when you do the Kelvin probe microscopy, then do a Casimir measurement, and then do Kelvin probe microscopy again, are the results reproduced or they change as a result of the having another surface in contact with this one?
Yeah, so I guess a few parts to this. So with the reproducibility, with bringing the humidity down and then bringing it back up, we do see some variations that they don't come back to quite the same value. So we're still trying to figure out why that is. With the measurements, that's what we're working on now, is trying to characterize both surfaces and then make Casimir force measurements to see how that varies. So I think that's a good question. It doesn't vary with time as well. That's something else we're trying to understand is, if we just look at these samples, we think our system is stable, do the patches vary with time? And so those are still open questions.
Okay, now,
Most rod like mounts that I know of, they're very flexible and out of like direction. Isn't that hard to take into account when you're measuring torque? Or perhaps you have molecules that are stiff?
Yeah, so with these,
How would you do that?
yeah, so with these liquid crystals, they're fairly well known, fairly well characterized, and you can make them so that they basically are in plane, depending on how you coat the surface. And so we're making them in plane on one of the surfaces, and then they basically will continue to be in plane throughout the bulk of it until we get to the other
So
surface.
they have to be aligned somehow?
Yeah, so what we're doing is we have one surface where we align them, and then the other surface is, there's no alignment unless we have a strong torque or something like that. So the idea is that you align them on one surface, and then they would just basically stay aligned, and we've seen that basically happens. And then the question is, if you bring in something that could cause the alignment to change, say like this, due to a torque, does the crystal rotate to find some new alignment? But it basically stays in plane. But there's a lot of surface preparation you have to do in order to make that happen.
okay, I think we should probably conclude. So let's thank all the speakers of the morning session here.